So I'm going to talk on an algebraic approach to non-malleable commitments, and this is a joint work with Vipul Goyal, Silas Richardson, and Alon Rosen. So let's first recall what's a commitment scheme, and this is a digital analog of locked boxes. So it's a two-stage process between a committer and a receiver, where in the first stage, the committer will put a piece of paper inside the box, lock it, and give it to the receiver. This is called the commit stage. In the second stage, the committer will send over to the receiver the key that enables the receiver to open the box and see what's inside. This is called the reveal stage. And both of these stages can be interactive also. So formally, a commitment scheme is a two-stage protocol between a committer and a receiver that has the following properties. The first property is hiding. It means that for any two messages, the receiver cannot distinguish between a commitment to M1 and a commitment to M2. And the second property is binding. It means that the committer cannot open the commitment to a value that is different from the value that determined at the end of the commit phase. So there are two notions of commitment schemes. One is statistically binding, and it means that the binding property should hold against unbounded committer, and the other one is computationally binding, that considers a computationally bounded committer. So we will concentrate on the statistically binding commitments, and it is known that we can construct statistically binding commitments from any one-way function. However, we also know that standard commitments are not always enough for applications. And let's remind ourselves the issues. The problem that we will see now is input independence. The first example is auctions. Let's say we have two bidders, bidder number 1 and bidder number 2, that are about to bid on some item, and we want to ensure that their bids are independent. So first, bidder number 1 will commit to his bid, and then bidder number 2 will do the same. We know that bidder number 2 would love to set his bid slightly higher than the bid of bidder number 1. And if we examine the definition of commitments, we will see that nothing there rules out this behavior. And in fact, bidder number 2 can break the protocol without breaking, hiding, or binding. So for many natural commitment schemes, if we'll use them here, bidder number 2 will be able to make some dependencies between the bids. Another example is multi-party computation. So it's a more general example. We have, let's say, two parties that will commit to their inputs and later perform some computation on it. What we want to ensure is that their inputs are independent. And we want also to have a protocol that will enable them to commit or compute simultaneously. Moreover, we would like to support multiple parties. So the question is, how can we make it efficiently? One way to achieve input independence is by non-malleable commitments. And this was introduced by Dolev Dvorak Naor in 1991. So in this setting, we have a man-in-the-middle adversary that receives a commitment on the left and commits to some value on the right. And the goal of this man in the middle is to commit to a related value, and by doing that, to harm the security or the correctness of a big protocol. So we would say that a commitment scheme is non-malleable if there is no man in the middle that can commit to a related value. And we should note that in this definition, there is no opening of the commitment. So the value that the man in the middle commits to must be uniquely determined from the transcript. Otherwise, it's undefined. It's not well defined. And for applications such that the multi-party computation, where you just commit to the inputs, make some computation, but never open the commitments, this notion seems to be suitable. There is another notion that's called non-malleability with respect to opening, where it guarantees that the man in the middle cannot open the commitment to a related value, but he might be able to commit to a related value without knowing how to open it. Okay? So more formally, we'll see the definition, and we'll use a definition of Pass-Rosen. This is a stronger definition. It's with respect to indistinguishability. And actually, we'll use the definition of Lin-Pass, but they're the same. So again, we define non-malleability via the simulation paradigm. In the real execution, we have, as before, the man in the middle that receives a commitment on the left and commits to some value on the right. In the ideal execution, we have a simulator that has no left interaction and only commits on the right. And what we want to guarantee is that for any man in the middle, there exists a simulator such that commits to essentially the left, that commits essentially to the same value as the man in the middle. And this would capture intuitively what we want, because the simulator has no left interaction. And if he commits to the same value as the man in the middle, it means that the value of the man in the middle is independent of his left interaction. So formally, we define non-malleable commitments as, for any man in the middle, we have a simulator such that the view of the man in the middle in the real execution and the value he commits to will be indistinguishable from the simulated view that outputted by the simulator together with the value that the simulator commits to. So we should note that the value m tilde is not outputted in the clear in the real execution, and it's inefficiently computed from the view, but inefficiently. So now, what the definition I will use is with respect to tags. It means that every participant has an identity, and this is equivalent to a definition without tags called non-malleability with respect to content. So it's just for simplicity, nothing new. Okay, so I'll briefly review what we have with what constructions we have with non-malleable commitments. So the first one is DDN. It was a log n rounds from one-way function. Then there is a protocol by Barak that made it constant round, but used trapdoor permutation and collision-resistant hash function. Later on, Pass-Rosen showed a constant round protocol that uses only collision-resistant hash function. In 2010, we presented almost constant round. It was log star n rounds protocol from any one-way function. And recently, there is two protocols by Lind, Pass, and Goyal that give constant round non-malleable commitments from any one-way function. And the constant is above 10. Okay? So in this work, what we will see is 4 rounds non-malleable commitments from any one-way function. And the protocol is very simple, it is efficient, and in fact, we're implementing it right now. So,
is there any tightness claim, or what's the smallest possible number of rounds?
That's a good question. I don't know, maybe we can do in 3 rounds. I don't know. Okay. So first, I would like to show you, first attempt, a mini version of our protocol, and it will be a malleable version, but by inspecting it, we will see what's exactly the components that we will need in order to make it non-malleable. So, as we said, the committer has an identity ID. It will be in the domain of 2 to the k, and he will want to commit to a message m. What he will do, he will sample a random value in ZQ and define a polynomial fx to be equal rx plus m. Then he will commit using some statistically binding commitment, like an OR commitment, to the coefficients of this polynomial and send it over to the receiver. The receiver will sample a challenge in the domain of 2 to the ID. So the challenge is dependent on the domain of the challenge is dependent on the identity of the committer, and send it over. The committer will first check that the challenge is drawn from the right domain, and if not, he will abort. Otherwise, he will just evaluate the polynomial and send the evaluation to the receiver. Lastly, the committer and the receiver will engage in a zero-knowledge proof of knowledge, showing that steps 1 and 3 are correct. And so the statement that we're going to prove is that there exists a message, M, a randomness S, a value R, a randomness SR, such that the commitment in the first round, the commitment to M is commitment to M using S, the commitment to R is the commitment to R using SR, and the evaluation in the third round is the evaluation of F on the challenge alpha. Okay, and I would like to check what happens to this protocol when we run it with the simplest man in the middle possible, the copying man in the middle. So the committer has identity ID, and the man in the middle has identity ID tilde. Let's assume this does not have to be true, but let's assume that ID tilde is greater than ID. So the man in the middle will receive commitment to M and R. What he will do, he will add 1 to the commitment to M and forward the commitment to R as is. Now he will receive a challenge alpha tilde that is drawn from 2 to the ID tilde domain. In order to answer this challenge, he must copy this challenge to the left. Otherwise, he don't know the commitment, so he cannot answer it. But the problem is that it might be the case that he won't be able to copy it. Why? Because ID tilde is greater than ID. It means that 2 to the ID tilde is at least twice bigger than the domain of the left side from where the challenge should be drawn. So the probability that alpha tilde will match the left side is at most half. So in this case, we can see that alpha tilde will be illegal with overwhelming probability. But the problem is that ID tilde does not have to be greater than ID. So how can we do it? One approach would be to use the 2-slot trick, similar to pass-Rosen, where you take the ID and just one repetition would be with this ID, one would be n minus the ID, and then one of them will be bigger than on the right than on the left, and you will get this. But, sorry?
Can you slow down a little bit?
Yes.
So I understand that now you're exploiting the fact that the challenge space is kind of different between the two rules.
Yes.
But I don't understand something much simpler, like, so you're committing to a hash function in the same, pairwise independent hash function, right? I mean, why do you do this polynomial? Or where does it come from?
It's a line, it's just a line, right?
Yeah, okay, sure, but what's the intuition? Why do we commit to a line? I guess that it's something about rewinding or
yes, because I can extract from it.
Okay.
It's easily extract, right? It's enough 2 points to interpolate, but in fact, we will need more.
It's kind of a sigma protocol or something.
Exactly, and that's the way also to instantiate it. Yes. Okay, but so the 2-slot trick can be applied, but it will blow up the round complexity here. Okay, so what we want to do is to find a way to do the same, to make ID tilde to be greater than ID without blowing up the round complexity, to stay with the same number of rounds. Okay, and we do it in 2 steps. So we derive tags T1 up to Tn from the identity ID of k bits. First, we apply error-correcting code, and we obtain a vector of n over 2 entries in ZP. So we will apply an error-correcting code with constant distance, and this will give us the following. If 2 identities are different, then when we look on the code words after the error-correcting code, we will have that a constant fraction of the entries will be different from all the entries of the other ID and vice versa. And this is similar to the DDN log n trick, but instead of having just one entry that is different from all the, at least one entry, we're guaranteed to have a constant fraction. Okay? The second step would be to take these elements after the error-correcting code and just add them to some value. So we have n over 2 elements. For each element in entry I, we will add 2 times pi to it, and we will obtain tags T1 up to Tn over 2 by doing that. And to get the other n over 2 tags, we will just take the appropriate tag from the first n over 2 and subtract it from 2n plus 1 times p times I. Okay? And this is similar to the 2-slot trick, but this will enable us to do all the repetition in parallel instead of doing it sequentially. Okay?
So what's the combinatorial property that you get?
Exactly, that's what I'm going to show now. So this tag has some properties that are crucial for our proof. Okay? The first thing is ordered. You meant these properties like that, right?
Yeah.
Okay. So the first property is ordered. The second property is that they are well spaced. If we look on any 2 tags, they will be far apart, at least omega of log gamma, where gamma is the security parameter. Okay? The third thing is that if we look on two sequences of tags that resulted from different IDs, for any I differ from j, ti would be different from tj tilde. It means that if you look on two sequences and look on entry I versus entry j, they will be different. Okay? And if we look on the same coordinate, they will be different for a constant fraction of them. Okay? And not just different, they will be balanced. It means that a constant fraction will be bigger for the first one and a constant fraction will be bigger for the second one. It's not that one of them, all of them will be bigger in one of them. Okay? So now we can see our protocol and see how we use these tags inside it. So now we have, instead of identity, the tags t1 up to tn that we generated. And the committer, in order to commit to a message m, will draw n values from zq and define n lines instead of one line. Okay? He will define fi of x to be ri of x plus n. He will commit to all of these ri's n to m. The receiver will sample now n challenges instead of one challenge, where each challenge is drawn from a different domain. And this is crucial. Okay? Each challenge, alpha I, is drawn from 2 to the ti. Okay? So he will sample n challenges, send it over to the committer. The committer, again, he will check that the challenges are drawn from the right domain and evaluate the n polynomials and send over the results. And then they will do the zero knowledge step. So before proving that this protocol is actually non-malleable, by the way, the proof is complicated. The protocol is very simple. So before showing, let's go back to the copying MIM in the middle and see if we actually manage to prevent this attack, at least this attack. So we have tags t1 up to tn and t1 tilde up to tn tilde that belong to the man in the middle. So the man in the middle will receive a commitment to m, commitment to r1 and up to rn. He will add 1 to the commitment to m, and the rest he will forward as is. Now he will receive n challenges, alpha 1 up to alpha n tilde, and he will need to copy all the n challenges in order to answer these challenges. He will need to copy all of them to the left. But the problem is that now we are guaranteed that there is a constant fraction of ti tilde that is bigger than their corresponding tags on the left. And it means that for each one of them, with probability at most half, he will be able to copy. So in overall, the probability that he will be able to copy this challenge vector will be negligible. Okay? So against man in the middle that copies everything, we can handle him. But in general, it is much more complex to do it. Is there any questions? Because I have time. It's okay? Okay. Great.
Before com is any one function-based commitment, right?
Yeah, statistically binding.
Statistically binding.
Yes, anyone. Yeah.
So you need any initialization for this?
So if I use no, yes. So I'm hiding it for it to be simpler. But yes, we have another round with no commitment, of course. Okay, good. So let me just remind you what we need to do in order to prove that this scheme is non-malleable. We need to construct this simulator that will output a simulated view and commit to some value, such that the view and the value he will commit to will be indistinguishable from the real execution. So the simulator is very simple and is actually the standard simulator in non-malleable proofs. So he will just run the man in the middle internally, commit to 0, and output the interaction, and forward the interaction on the right to the external receiver. At the end of this execution, he will output the simulated view of the man in the middle, internal man in the middle. So if S is not a valid simulator, by definition it means that there is a distinguisher that upon receiving the view and the message committed on the right, he will be able to distinguish the real and the ideal execution. And in particular, it means that this distinguisher can break hiding, because in the simulated execution, the man in the middle received a commitment to 0, and in the real execution, he will receive a commitment to some other value. So in general, we can use this distinguisher in order to break hiding. Let me tell you how we construct an adversary that breaks hiding in case the simulator is not a good simulator. So the adversary will receive a transcript that belongs either to the real or to an ideal execution, both sides of the transcript, both the left and the right side. He will forward it to the extractor that will squeeze out of it the message committed on the right by the man in the middle. And the message and the view will be forwarded to the distinguisher that will output either real or ideal. And the probability that this adversary will succeed is the probability of, let's say, it's the overlapping between the distinguisher probability and the extraction probability. Okay? So what left to show is the extractor. Okay? Now we need just to show the extractor. Let's assume the following. Let's do the following extractor. The extractor is given a main transcript as the adversary. And what he will do, he will rewind to the challenge phase and feed the man in the middle with a new challenge, beta 1 tilde up to beta n tilde. Okay? Now, the man in the middle will give on the left a new challenge on the left. And the problem is that the extractor now cannot answer correctly on this challenge. So what he will do, he will just give random answers. Okay? Now the man in the middle will give us answers on the right, beta 1 tilde up to beta n. And potentially, now the extractor has 2 points for each coordinate. So potentially he can pick some coordinate and interpolate the line and extract m tilde. That's potentially. But the question is that m tilde correct? What guarantees me that it will be correct? Nothing. The difference now, in the main thread, the man in the middle provided zero knowledge proof of knowledge on the right. And now there is no zero knowledge proof of knowledge. And moreover, the extractor feeds the man in the middle with random answers. So it might be the case that the man in the middle just gives all the answers incorrectly, and we will interpolate the wrong line and extract the wrong message. Okay? So as I said, there is a problem. If m is incorrect, the extractor will just output garbage. The solution to that would be to rewind twice and check collinearity. So let's say that we rewind it twice, and this is 1 point of the rewind that the man in the middle gave us in the first rewind, and this is for coordinate I. We have n coordinates like that. So, yes. So here we rewind it once. So he will do it again. Okay? Note that he won't complete the zero knowledge proof of knowledge. He will just rewind. Okay. So he will rewind twice and check collinearity. So let's say for coordinate I, this is the answer in the first rewind, and this is the answer in the second rewind. And this is define some line, right? And if one of them is incorrect, this will define the wrong line, right? So let's look. And this is the correct line that defined by the commitment. And this is not going to change because we never change the commitment. We rewind only to the challenge step. So there is only 1 point that will be collinear with the incorrect line, right? Only this point will be collinear and will pass the test with this incorrect line. So in order to pass the test of the collinearity, it must be that this is the point that was asked in the main thread, in the transcript that he received, right? And what we show is that m will answer incorrectly but collinearly with negligible probability. Why? Because the probability that this is the point that is asked in the main thread is negligible. Okay? And this concept will be back again later. So what we have right now is that if we give correct answers to the man in the middle, he will be correct. And the reason for that, if he's incorrect on correct answers, the dummy simulator that just aboard will be a good simulator, okay? So it must be the case that given correct answers, m is correct. Fine? Okay. But the extractor gives random answers. So it might be 2 cases. M might be correct in at least 1 coordinate. In this case, we can easily extract. We go every coordinate, look for collinearity test, found 1 collinear, goodbye. we're done. But what if he answers incorrectly everywhere? So what we show is that it cannot be. If M is incorrect, E will fail, and we show that we can use this M to break the hiding of our protocol. Okay? Is there any questions? No? Okay. So to do so, we examine all the ways that the man in the middle can make dependencies between the commitments. Okay? And let's assume that the man in the middle takes the commitment to Ri prime here, some Ri prime here, some commitment, and mulls it into a different commitment somewhere here. Okay? What it means when... Sure.
So the problem is because you have many R's. So what if can't you just do it with one R like you did in the beginning? Would that be a problem with like the correctness, or what's the...
Sorry.
Why can't I just do it with one R, like in the sort of dummy example that you showed in the beginning? You said the problem is that in some, there could be like a dependence between them. So why can't I just use one?
Because I must have the tags, like enough tags to be bigger, right?
But then, so just with some, what is, if I just have one, it's going to give me some weak property, like with some probability it will be non-malleable or something like that.
Oh, yeah. If you have the promise that the one on the right is bigger, right? Like the tag of the man in the middle is bigger, so you cannot match the challenges all the time, right? That's what you're asking.
Okay, yes.
So you will have, if it's really big, then you will have really small probability to match the challenges to the left, right?
So if I'm always guaranteed that the tags are in the right order, that the man in the middle, that the sort of the tag that I'm trying to forge is like smaller, then just one is enough.
So if you can make the man in the middle to have a tag that is much bigger than the tag of the committer,
yes,
you're done, right? Because the probability that you'll give him a challenge with high probability it will be out of the range of the left challenge, and you're done. But I don't know how to do it. That's the problem. Because you need really bigger, not twice bigger. You need and also this will affect your.
The question is the order, I guess.
Yes.
So can you describe it like two different protocols? One with this property we just described, and one that's basically use a recursion code to combine this small protocol into a protocol of high security. Can you give such a I mean, you have one protocol that's claim that if you have this guarantee, you have a non-malleable commitment for everything, and then use recursion code to combine it.
You mean to make this guarantee happen, right?
Yes. Yes.
So I think in general.
Two dependent steps, like one user recursion code.
Yes.
Combine one step.
Yes. In general, yes. So I also.
For what we care here for this part, we can only care because there's only one commitment. One M and one R.
Yes, as long as you can guarantee that. But
no, but now the problem is that if you try to do it again, if you try to do this sort of parallel repetition of things, then like there can be a dependence, and then
right.
you can sort of screw up more than one in like a non-trivial way, right?
Right.
So you have to show that.
And
it's kind of like a parallel repetition thing, right?
What you want is to have one protocol and then apply error correcting code and repeat it, like. Right. So similar to what we do, right? So in general, you can apply error correcting code to get this guarantee, and yes, in general, but you need to be careful with what you plug in inside. Okay. And also I wanted to tell you about the tags. To have a tag that is very big compared to the other tag will affect your communication complexity. The challenge would be huge, right? And we also don't want to do that. We'll want to stay like minimal. I mean, yeah, if you have the tag here, it will be, the tag will be, if you have a tag very big here and much smaller here, it will be huge, right? The challenge will be huge.
But you're duplicating it n times, that's also kind of...
Yes, but I'm saying in general, depends. You need to take a look at it. So, in fact, it would be interesting, and we're trying to do it, to make the domain smaller, okay? Because it's still big. Okay. No, it's okay. Okay, so let's say that he mulled some commitment here into a commitment here. So now when he gets the challenge, again, he must mull the challenge for the appropriate commitment into a challenge here. Same way. And it means that this challenge is dependent on this challenge. Okay? So we define an epsilon dependence to be alpha I prime is epsilon dependence on alpha I tilde if the probability when we fix this will be fixed is at least epsilon. And it is important to say that these dependencies are defined by the dependencies the man in the middle does in the commitment phase. And because we never change the commitment, these dependencies are fixed during the extraction. Okay? So if one challenge depends on the other challenge, it will stay dependent in all the rewinds. Okay? Fine. So what we now will do, we'll just examine all the ways that the dependence can happen. The easiest way is in dependency. It means that there is some coordinate on the right that has nothing dependent on it on the left. Okay? We'll fix this. Nothing will be fixed on the left. So for this case, we show that if M has this kind of dependency, then we can break the hiding. Another kind of dependency is 1 to 2. It means that we have two coordinates on the right, such that I'll fix this. This will be fixed. I'll fix this. This also will be fixed. Okay? It doesn't mean that I need to fix them together, right? Each one of them, when it will be fixed, the left one will be fixed. So also for that, we can break hiding. The third one is if I have unbalanced dependency, if I have a coordinate that is on the right, that is bigger on the left, it also will break hiding. And the one that left is what if it's neither of those, it will also break hiding.
So back to Rita and Vald's question. So don't you prove here a power repetition theorem for the non-malleable commitments? Like ignore the order issue. Say that I have a weak commitment, some 1 over poly probability of.
No, intuitively it's similar to what we do, but we don't prove it.
On the properties of the protocol.
Exactly. Yes, but it can be looked as boxes that you can fill inside. This, if you'll find a good definition for epsilon dependence for a different protocol, and you will manage under your definition to divide the domain of dependencies into some groups and show that each one of the groups break hiding.
Looks very general to me.
That's what I'm saying. Yes, but maybe for a different protocol you'll need a different epsilon dependence definition, and then maybe you'll have a problem for the new definition to divide it like that. We had tries that you could not divide the domain of all possibilities. And I'll just say we don't show directly that we break hiding. Sorry. We use our main technical lemma that we use to show that we break hiding is the following. We rely on the following. If you have a challenge on the left such that it has super polynomially many pre-images on the right, it means that there is super polynomially many challenges on the right that once they will be asked, exactly this alpha n alpha 1 up to alpha n will be asked on the left. Okay? So if you have this property in your transcript, then I can break hiding. I can construct an adversary that can break hiding if this is the property. And what we do is in all previous cases, except for this case, we show a reduction between these cases to show that the transcript actually has this one to super poly dependence. Okay? So the intuition why you can break hiding is that the answer to the left challenge won't be enough to answer all these super polynomially challenges on the right. It has there's no enough information just to answer them. So how we prove it, we construct an adversary that will check again collinearity, but now he will check the collinearity in all the coordinates. Before, the extractor needed only one coordinate to be collinear. He checked first, second. Here, we need it to be collinear in all the n coordinates. And part of the proof, we show that M will answer incorrectly but collinear with negligible probability. And in this case, this will rely on the fact that we have super polynomially many challenges here that will map to the same one, but only one of the super polynomially many challenges will make it collinear. That's what we show in the proof. Okay? So also, if somebody wants to use similar ideas to ours, this lemma needs to be proven. Okay? You need to divide your domain into these cases and make a reduction from these cases to show that this is the case. And this is not always true, depending on your scheme. So let me just tell you other properties of our protocol. So it is binding, of course, because the commitment we use is statistically binding. Hiding comes from the hiding of the commitment, the zero knowledge. And the challenge response that we reveal only 1 point in each line. So it's like 2 out of 2 Shamir secret sharing. Round complexity. I promised 4 rounds, but I showed something like 8 rounds. Okay? So how we do that? We take the zero knowledge protocol and we lift it up and perform it parallel to the commit challenge response phase. And we use a similar variant of Feige-Shamir, but we use it based on one-way function. It's something different. And we can, of course, do non-malleable zero knowledge by committing to the witness and slightly changing the statement here. And lastly, we can do also sigma protocols. We'll change it to El-Gamal commitments. This will be Schnorr protocol. And because of the homomorphism of the commitment, we can apply also multi-batch verification and multi-exponentiation. So it will be very efficient. Okay? And let me just summarize. We have a new approach to non-malleability. We combine all techniques and new ideas. It results in a very efficient protocol. So there are many open problems, but just few of them can we do in 3 rounds, a black box in 4 rounds. If I want to make our protocol black box, I can use Goyal et al. Solution from 2012, but this will add me 2 more rounds. So I don't know how to do it in 4 rounds. And in general, it would be nice to have more application to constant round and multi-party computation. Questions?